Okay, I think we can start. Okay, welcome everyone. Welcome back from the study break. Well, I hope you used the last week to do a little bit of revision of like whatever we have seen so far, at least the last lecture, so that you did not forget where we stopped. Okay, so let's get started. Let me share my screen. Okay, so let's start with a quick recap of where we stand in the course. Like maybe to go even beyond the previous lecture, like so we started discussing about classification models, and like we started with probabilistic generative models, and then like in the previous lecture, like we actually looked at these generative models. Like for example, in the case of two-class problem, it's going to be sigmoid of W transpose X plus W0. In the case of multi-class, it's softmax, right? And usually, like if you have a Gaussian assumption in the case of GDA, you're going to have some equation to represent the W and W0, right? So it was represented as a function of mean variance and prior probabilities. So we discussed that this assumption that P of X given Ck is Gaussian could be limiting and it could not hold all the times. So a simple alternative for such generative models is the idea of discriminating models, where like you are directly trying to model probability of Ck given X. And the way in which we are going to do that is by actually treating these W and W0 as parameters instead of having extra functional form for those, right? Like so, and that was logistic regression model, right? So logistic regression is like a very simple classifier where the probability of C1 given X is given by Y of X, where Y of X is sigma of W transpose X, right? So now we added this sigmoid function on the top of the linear model so that the probability is between 0 to 1. And this is a very simple classifier when compared to GDA because this has only m plus 1 parameters, right? Like so if you have m features. And we also discussed how to learn these parameters by using the maximum likelihood approach, right? Like so, like we first computed the probability of t given w, and then we computed the gradient for this. I mentioned that there's no closed form solution for this, so we started doing gradient descent, right? Like so now since we have likelihood, and normally in gradient descent, like you want to minimize something, so like instead of maximizing the log likelihood, like we were minimizing the negative of the log likelihood. So that is what this term is, right? And to compute this gradient, we use the chain rule, right? Like so, because it's a function of function of function, right? So like we use the chain rule, and then finally we arrived at a gradient equation like this, right? So we stopped the lecture with this observation that the gradient for logistic regression actually looks very similar to the gradient for linear regression, right? Like, so if you remember, like in the case of linear regression, we were doing least squares error, like we were using least squares, right? Like, and in the case of least squares, you have the sum of square error function, and you're trying to minimize this error function. And like in contrast, in the case of logistic regression, we have negative like negative log likelihood, and we are trying to minimize the negative log likelihood, right? Like, or in some or in other words, like you're maximizing the log likelihood, right? So now I stopped here saying that this connection, like the similarity between these two solutions, is not a coincidence. So in today's lecture, we are going to start the lecture by like digging deep into this connection, and then like further discuss more about logistic regression. Okay, so is there any questions before we start, given that there was a 1 week break? Any questions? No? Okay, so there is some chat. Okay, so the cost function is convex in this case. Yes. So we will discuss about that probably in 10-15 minutes. So we are going to discuss more about that. But your observation is right. Okay, so there's another question. So Emily typically proceeds with two steps. First, we choose the type of distribution our data is sampled from. Second, we set the parameters of this distribution so that the observed data is as likely as possible. Okay. Okay, so this means okay. So this Michelle, I think it's more of a comment. So like whatever you ask in the chat is exactly what we are going to discuss as the first part of the lecture. So maybe your question or comment will become more clear after we do that. Okay, so I think people want to jump into the connection between maximum likelihood and least squares. So let's actually get started. So we are going to discuss about the connection between maximum likelihood and least squares. Okay, so to give you some idea, in the case of least squares, we had a non-probabilistic model, right? It was a simple linear model, just wx plus b, right? So, and in the case of the logistic regression, we were doing maximum likelihood. So let's call this as regression, and this is logistic regression, okay? We are doing maximum likelihood with a probabilistic model. Okay, so now let's actually go back to linear regression and look at it from the probabilistic perspective. Okay, so now assume that the target variable t that we have for the linear regression is given by some deterministic function. Okay, so t is equal to y of x given w. Okay, and let us assume that there is an additive Gaussian noise to this. Okay, so plus epsilon, where epsilon is a zero mean Gaussian random variable. Okay, with precision beta. Okay, so precision is basically inverse of variance. I could either use variance or precision. Okay, so now the moment I assume that there's a Gaussian noise added, okay, now I can ask this question, like, which is what is the probability of t given x, w, and the beta, right? So now this is like you're adding a zero mean Gaussian noise, right? So then basically t becomes a Gaussian centered around y, right? Like so the target. So it's basically it's a Gaussian distribution given where the mean is given by y of x comma w and the variance is given by beta inverse. Is that clear? So all I have done is I assumed that in the case of linear regression, there is going to be a Gaussian noise added to the target. So then the probability of t given x, w, beta becomes a Gaussian distribution with mean y and variance beta inverse. Okay. So now I can actually take the entire data set xn tn for n is equal to 1 to n, right? So now we can ask what is the probability or likelihood of this data set, right? Like, so you see where I'm going. Like I'm trying to come up with a probabilistic version of linear regression, and I'm trying to do maximum likelihood for that, okay? So now the probability of t given x, w, beta is given by, there are n examples. So product of n is equal to 1 to capital N, Gaussian, right? So T of n given W transpose xn, which is the y, comma beta inverse. Okay, So let me actually take this to the next page. So this is the likelihood. Now we can compute the log likelihood, right? Like, so the ln P of t given xw beta is given by the product becomes summation. So summation over n is equal to 1 to capital N ln Gaussian. Okay, so now you know the PDF of Gaussian distribution, right? Like, so now the mean mu is given by W transpose X and the variance is given by beta inverse. So when you substitute the PDF of the Gaussian here, you are going to get something like this, okay? Ln beta minus n by 2 ln 2 pi minus beta times ed of W, okay? Where ed of W is given by 1 over 2 summation over n is equal to 1 to capital N Tn minus the mu, x minus mu the whole square. So x minus mu the whole square. Okay, so now we are maximizing this log likelihood. Okay, now you can see that the first term has nothing to do with W, right? The second term has nothing to do with W, so you cannot do anything with this. So maximizing the log likelihood is actually equivalent to maximizing this term, right? Or in other words, minimizing this term. So minimizing ED is exactly what least squares is doing, right? So hence, maximizing log likelihood, okay, with respect to W is actually equivalent to minimizing ED of W with respect to W. Okay, so doing maximum log likelihood and least squares are exactly same if you assume that the noise is Gaussian. Okay, is that clear? Okay, so now a couple of points to remember. Okay, the first no. So in the case of squared loss function, okay, so can someone remind me what is the optimal predictor for squared loss? So this is from probably lecture 2 or lecture 3, right? Like, so we discussed that, like, if I have a squared loss, then this will be the optimal predictor for regression. So can someone remind me, like maybe in chat or raise your hand? So what is the optimal predictor for squared error? Okay, so any answer? Okay, so, oh, no, I'm not asking solution for linear regression. So I'm asking what is the optimal function that one could like one could consider for like when you use squared error, right? Yeah, so yeah, like, okay, so I think a couple of you have got it right. So basically it's conditional mean of like it's a conditional mean of y, right? So like it's probability of y given x or t given x, right? So it's like when you have a squared loss function, the optimal prediction is given by conditional mean of target variable. Okay, so now if we use the Gaussian assumption, the Gaussian noise assumption, then that basically means that the probability of t given x is Gaussian. Okay, so now we know that a Gaussian distribution is a unimodal distribution. Now, this is going to be not appropriate for some applications, like where it's too much of a simplification to like consider P of t given x as unimodel. Okay, so now this is the limitation of using Gaussian noise like with least squares. Now, the second note is, so now we can actually try to reason why least squares is bad for classification. Okay, so remember when we started doing classification, like we wanted to borrow whatever algorithm that we have learned in linear regression. So we were doing least squares for classification, right? So now this Gaussian interpretation actually tells us why least square is bad for classification. It's bad for classification because in the case of classification, t is a binary variable. The target is a binary variable, right? So now this binary distribution, like this is going to be very different from the Gaussian distribution. Okay, and hence the bad performance. Okay, so this probabilistic view of least square also tells us why least squares is a bad idea to do for classification. Okay, so now that is like an interesting connection between least squares and log likelihood, like the maximum log likelihood. Okay, so now let's get back to logistic regression. Okay, so now there was this question in the beginning about whether this loss function is convex or not, right? So we're going to get into that discussion now. Okay, so now in the case of least squares with linear regression, right? So we had a closed form solution. Remember? So I think some of you even pointed out the solution in the chat, right? So the closed form solution was x transpose x inverse x transpose y, right? Like, so we actually had like a closed form solution to implement in the case of least squares with linear regression. So why was that the case? So why is it that I got a closed form solution for linear regression, but not for logistic regression, right? So we also discussed a bit about the reasoning for that, right? Like in the case of linear regression, because in the case of linear regression, the error function was a quadratic function of parameters, right? So it's a quadratic function. So we were able to come up with a closed form solution in that case, right? Like on the other hand, in the case of maximum likelihood for logistic regression, okay, there is no closed form solution. Okay, so now why? Why is there no closed form solution? Because in this case, the error function is actually a non-linear function of W, okay, which is not quadratic. It's not a quadratic function, but it is some non-linear function, okay, and this is mainly because of the sigmoid activation function that we are using, okay. Now there is a good news. So in the case of logistic regression, the error function is not a quadratic function, okay, but it is still a convex function, okay. And you should have had some reading about convex functions in the previous weeks, right? Like, so the one of the nice properties about convex functions is the moment you know that a function is convex, you know that there is actually a unique minimum. Yes. So there is someone asking, can we use gradient descent? Yes, that's why we had a gradient descent algorithm for logistic regression in the previous lecture, right? Like, so now this fact that like there's a unique minimum and it is a convex function tells us that if you're going to use gradient descent, you are going to converge to the global minimum, right? So you do gradient descent with the update equation that we learned from the previous lecture, like you're going to reach the global minimum. Okay. So now when we realize that this is actually a convex function and there's only one global minimum, okay, there are actually many other algorithms than gradient descent, like which exists and which is faster than gradient descent. Okay, so now we like for today's lecture, like we're going to discuss about like one more algorithm than gradient descent. Okay, so we're going to look at a more efficient method than gradient descent, which is basically the idea of Newton-Raphson algorithm or Newton-Raphson method. Okay, so some of you might have seen Newton-Raphson already in some of your previous courses, like sometimes in numerical methods and sometimes in other courses. Okay, so we are going to look at like how can we use Newton-Raphson method for learning the parameters of logistic regression. Okay, so now like gradient descent, this is also an iterative scheme. Okay, so this is also going to be an iterative algorithm. Okay, so now the basic idea in Newton-Raphson method is it uses a local quadratic approximation to the error function. Okay, so even though the error function is not quadratic, Newton-Raphson is going to make an assumption that locally the error function is quadratic. So now the moment you say that this is locally quadratic, you can solve it in one step, right? So and you reach the minimum. Now from wherever you reached, again, you make another quadratic assumption, reach the minimum, and you continue. So that is the idea, okay? So specifically, we're going to take the error function, okay, and expand it by using the Taylor series. Now we are going to expand it and stop at the second order approximation. Okay, so now E of W can be approximated as E of W0, like at some point W0, okay, plus W minus W0 transpose the gradient. Okay, so this is the first order approximation, right? Plus 1 over 2 W minus W0 transpose H W minus W0. Okay, so where H is basically the second order gradient. So H is the Hessian of E with respect to W, evaluated at W0. Okay, is that clear? Okay, now we are going to take the error function and we are going to approximate the error function using this second order Taylor series expansion. Okay, okay. So now let's actually cut paste this error function and differentiate it with respect to W and see what happens. Copy. Okay. Okay. Now, this is the second order Taylor approximation, and we are going to differentiate this function and set it to 0. Okay. So you differentiate the first term, it becomes 0, right? Because it's a scalar. Plus, you differentiate the second term. So you have W times gradient. So it's just the gradient, right? Plus, you differentiate the third term, it's W square. So 2 times W, 2 cancels, right? Like it's just W multiplied by the Hessian. So it's just W minus W0 transpose Hessian is equal to 0, right? So now W minus W0 transpose Hessian is equal to minus gradient. Okay. And W is given by minus okay, so maybe I'll do, let me not skip the step. So I'll just do W minus W0, okay, is equal to minus H inverse of gradient. Okay, so now W is given by W0 minus H inverse of gradient. So The update equation for Newton-Raphson method is basically W new is equal to W old minus H inverse of the gradient. Okay, so now this is Newton-Raphson. Now let's actually compare this with the gradient descent update equation, which is basically W new is equal to W old minus alpha times the gradient. So if you remember, so this is gradient descent, right? So now you can see that, okay, the first observation is there's no learning rate or step size in Newton-Raphson. So, right, in the case of Newton-Raphson, no step size, which is a nice thing because in the case of gradient descent, learning rate alpha is always problematic because if you have too small alpha, you're going too slow. If you have too big alpha, then you're diverging and so on, right? Look, so you don't have that issue in the case of Newton-Raphson, okay? On the other hand, Newton-Raphson expects you to compute inverse of the Hessian, okay? So now Hessian is a huge matrix because if you have n parameters, it's going to be an n cross n matrix, right? And you have to invert this Hessian, which might be a computationally intensive operation. Okay. Okay. So now, before we discuss further about that, so a quick note. Okay. If the error function is quadratic, okay, if my error function is quadratic, then the Taylor series expansion is not an approximation. It is actually going to be an exact equation because there is no third order term in a, like in my approximations. It's going to be an exact. It's going to be an exact um, exact expansion. Okay, so and hence the Newton-Raphson will actually find the solution in one step. Okay, so if you have a quadratic error function and you apply Newton-Raphson, it is going to find the error, like it is going to find the parameters in one step. Okay, so now let's actually verify this with linear regression. Okay, I'm going to do linear regression, and remember that in the case of linear regression, the error function is given by 1 over 2 summation over n is equal to 1 to capital N W transpose phi of xn. Okay, so I'm assuming a basis function model minus t of n, the whole square. Right? Okay, so now the gradient for this function is given by summation over n is equal to 1 to capital N W transpose phi of n. I'm just replacing phi of xn with a short form phi of n minus t of n. Okay, so x square is 2x, the 2 cancels. Now you differentiate internally. So W transpose 5 when differentiated gives you phi m. Okay, so now I can actually write this whole thing as phi transpose phi W minus phi transpose T in vector notation. Okay, so now the Hessian is given by the double derivative of the error function. So you derive, like you differentiate this again, once again with W. So the first term actually becomes phi transpose phi. The second term has no W, so it's 0, right? Okay, so now we have both the gradient and the Hessian. Now let's compute the Newton-Raphson update rule. So W new is equal to W old minus Hessian inverse of the gradient, right? This is Newton-Raphson. Now this is W old minus, okay, phi transpose phi inverse, the gradient. The gradient is given by phi transpose phi W old minus phi transpose T. Okay, so now this becomes W old. You do the first term, like you multiply the first term, inverse cancels, so it just becomes W old. Okay, Then you have plus phi transpose phi inverse phi transpose t, right? So now these two terms cancel. So we actually have the final, maybe I'll write it here. So W nu is given by phi transpose phi inverse phi transpose t. Now this is the one-step solution for linear regression. And this is exactly the solution that we obtained even using gradient descent. Like not gradient descent, the closed form solution, right? So the closed form solution can also be re-derived by using the Newton-Raphson method. Okay. Any questions? Okay, so there's a question which is, can we say that Newton-Raphson is always better than gradient descent SGD, even though the error function is quadratic or not? Okay. Well, it's in the case of quadratic error function, you're going to get one-step solution, right? Like, but in the case of non-quadratic solutions, you are going to get like it becomes iterative like gradient descent. So in general, Newton-Raphson is better than gradient descent because of like the fact that it is also using the double like the second order information. So we are going to discuss the geometric differences between gradient descent and Newton-Raphson like right after the questions. So maybe that will make it more clear for you. Newton-Raphson is better than gradient descent, but remember that it's also costlier than gradient descent because you have to compute this Hessian inverse for every time step, and that's a costly operation. And in the future, we will see models which has millions of parameters. So when you have million parameters, you cannot compute this Hessian. So in that case, like you cannot do Newton-Raphson, you can only do gradient descent. Is it implemented in scikit-learn? I'm not sure. Please check. But it's a standard algorithm. It should be there in scikit-learn. Okay, so okay, there are also some other previous questions like like why is quadratic important? Convexity is not enough. Well, so as we saw, if you have quadratic equations like that, like quadratic error functions, then you get a closed form solution. So that's why it's preferred over convexity, the convex functions. But at the same time, quadratic models which has quadratic functions are very limited in their power too. So it's a trade-off, right? The gradient should be evaluated at W0, right? Where? Okay, so the gradient here is evaluated at W or W0. I am not sure. I will think about it and get back to you. Okay, so let's continue. So now let's actually look at both the gradient descent and Newton-Raphson in geometric space. Okay, so versus Newton-Raphson. Geometric view to better understand like their differences. Okay, so now let's assume that this is my function. Okay, so to use the same function for both the algorithms, I'm going to copy the function. Okay, so now in the case, okay, this is my function f. Okay, now in the case of gradient descent, you start at a random point, okay, and then you make tiny steps to reach the minimum, right? This is gradient descent, right? So let's call this as gradient descent. On the other hand, what is Newton-Raphson trying to do? So Newton-Raphson, as I said in the beginning, like let's say you start here, it is first going to make a quadratic assumption in that space. Okay, so like it's going to make a quadratic assumption like this. Now you can find the minimum of this quadratic function in closed form, right? Like that is this, right? So now you project this to the function. Okay. So now look at like the beauty of Newton-Raphson. So instead of taking these tiny steps like all the way, like gradient descent, from this place, it actually jumps to this second dot because of its quadratic assumption. Okay. So now it again makes another quadratic assumption here. Okay. You find the minimum, you do the dot. Now this is the third. So another quadratic assumption, the minimum, and you continue. Is that clear? So now this is how, like this is a qualitative difference between what gradient descent is doing and Newton-Raphson is doing. Okay. So now we can actually look at this in the gradient space. Okay. So now, okay. So this is my cartoon explanation. So there might be some issues, but I guess not. But the basic idea here is this. So now this straight line is where f dash is equal to 0. Your gradient is 0. Okay. And you want to reach this point. Okay. Now this is my f dash. Okay. Now this is not, we are not in the function space. We are in the gradient space. Okay. Now this is a different type of view. In the gradient space, gradient descent actually takes one step at a time. It takes one step at a time until it reaches the place where f dash is equal to 0. Okay. On the other hand, Newton-Raphson, like if you are at this particular point, okay, it computes, sorry, it computes the tangent and use this tangent to actually reach the next space. Okay. So now from here, another, sorry, okay, another thing, and then you reach this place and so on. So finally, it will also reach f dash is equal to 0. Is that clear? So do you see the difference between Newton-Raphson and gradient descent? Okay, so yeah, so Guy, I think that is what I explained in the second view. Okay, so there's a question, can Newton-Raphson diverge? Okay, so, well, I need to verify, but I guess it cannot because there is no learning rate, right? So most probably it's not going to diverge, but please verify and let me know, like if you can quickly check now. Do you still have the risk of jumping to the minimum? Okay, so I think that Marsha's question is also the same thing. So maybe I could quickly verify Newton-Raphson. Okay, so okay, I'm not sure. So I'm going to verify and get back to you about this question, or maybe stay in the office hours. We could talk about it. Okay. Okay. So now that we have learned how to do Newton-Raphson, now let's go back to logistic regression and do Newton-Raphson for logistic regression. Okay. So now remember that in the case of logistic regression, the error function is given by minus of log likelihood, right? Like minus ln p of t given w, right? Now that was given by minus summation over n is equal to 1 to capital N Tn ln y of n plus 1 minus t of n ln 1 minus y of n. Remember? Okay. So now let's compute the gradient with respect to w. Oh, well, maybe we don't need to do that. Like we have already done that in the previous lecture, right? Like, so if you remember, the gradient was given by something very similar to the linear regression solution, which is summation over n is equal to 1 to capital N, y of n minus t of n multiplied by x of n. right? So if I have to write it in vector notation, it becomes x transpose y minus t. So this is something we already derived in the previous lecture, right? So now only thing we need to do as an extra step is to compute the second order derivative. So maybe it's easier for us to keep all these things in one place. So I'm going to copy this. Okay, now let's compute the Hessian. So the Hessian is given by double derivative, okay, which is basically, now just consider which one shall we take. So maybe consider this term. Okay, we are going to differentiate this again with respect to W. Okay, it involves a bit of chain rule, right? Because W, you don't see W directly here. So there's Y, which is a function of like W, right? So I'm going to do the rule, like I'm going to do the chain rule directly here. So summation over n is equal to 1 to capital N. Okay, now when you differentiate, the Tn term is going to like vanish. So it's just Yn times Xn. So there is Xn, which is going to say, now you differentiate Yn is sigmoid, right? So it becomes y into 1 minus y. So it's y of n, 1 minus y of n. Okay. Now you differentiate y. So now you differentiate inside the sigmoid, like W transpose X. When you differentiate, you get Wxn. Is that clear? So I have directly written this, like maybe to help you to do this derivation by yourself. So y of n is basically sigma of W transpose X. So when you differentiate this, you're going to get sigma into 1 minus sigma multiplied by, you differentiate W transpose X, you get X, right? So now this whole piece is what I have done here directly. Okay, so now I can actually write this as X transpose Rx, where R is an n cross n diagonal matrix. Okay, now where each entry of Rn is given by y of n 1 minus y of n. I have basically taken this whole thing and I have written it as a matrix notation, X transpose Rx. Okay, okay. So now you can see that the Hessian here is no longer a constant. It actually depends on W, right? So the first note, the Hessian is no longer a constant, okay? But it depends on W through R, okay? Which means you cannot get a single step solution for logistic regression. You're going to compute a solution which is a function of W, so you're going to iterate over it until W converges, okay? Okay, now there is also another note. Now we know that y of n, since it is a sigmoid, it's going to lie in the range of 0 to 1, right? It's because y is a sigmoid function, right? So this actually means that u transpose hu is greater than 0 for any arbitrary vector u, okay? Or in other words, Hessian is positive definite, okay? Now, if your Hessian is positive definite, then the function is a convex function. So now error function is a convex function of W, and hence it is going to have unique minimum. So this is why I said in the beginning that logistic regression actually has a unique minimum. Okay. Okay. So now let's actually write the update equation. So it's W new is equal to W old, okay, minus the Hessian, which is given by X transpose R X inverse, right? And the gradient, which is given by X transpose Y minus T. Okay. So now W new is equal to, I'm going to do a little bit of restructuring here. So I'm going to take X transpose R X inverse out. So this becomes X transpose R X times W old so that when you multiply them, the inverse cancels, right? Minus x transpose y minus t. Okay, so now I can rewrite this further as x transpose r x inverse, okay, x transpose r z, where z is given by x w old minus r inverse y minus t. Okay, so all I have done is like I have just restructured things so that this actually looks like the least square solution. Remember, the least square solution is x transpose x inverse x transpose y, right? Now this looks very much like the least square solution, except for the fact that you have this extra w, sorry, extra r, right? So this r is the weight that you are giving, okay? And hence this Newton-Raphson update formula for logistic regression is also can also be considered as a weighted least square. Okay, it's a weighted least square. Okay, but it's not a one-step solution. Why? Because R is actually a function of W itself. So until W converges, this update is going to keep on happening, right? So this is an iterative process. So this algorithm has a name in the literature. So this is called iterative reweighted least square. Okay, so IRLS is basically Newton-Raphson for logistic regression. Okay, I think we will stop here for the break. But before that, is there any questions on our discussion on logistic regression and Newton-Raphson? Okay, so the question is the chance NR stuck in local minimum more than GD? No. Well, I think no in the case of full gradient descent. But if you compare this with stochastic gradient descent can escape local minimas. Okay, any other questions? Okay, least square is a bad classifier only if you assume Gaussian. Uh, yeah, that's a good point. So the whole, well, also remember that the interpretation that least squares and log likelihood are similar or equivalent is valid only for Gaussian, right? So, and that is why I said least square is a bad classifier, because it has the Gaussian assumption in it. Okay, any other questions? Okay, so I will stop the recording. So we will go for like a 10-minute break and then continue.